The electrostatic force. An electron interacts with Ks 10 to the power of 20 times per second, and only a small fraction of the Ks will be involved in the formation of the electric field. Here we simplify it, showing 4K plus and 4K minus coming towards an electron. All 4K minus are absorbed, retained, and emitted. 3K plus are ignored and pass through without interacting. 1K plus is absorbed, its spin is turned, and it is emitted as a K minus. Thus we have 5K minus and 3K plus leaving the electron. So a homogeneous incoming flux of 8Ks is transformed to a flux with a surplus of K minus and a deficiency of K plus. The electron does not change the density of the K flux. It alters the composition of the spin distribution of Ks. Now we simplify the presentation further by letting the Ks move in one line, which is not correct but easier to illustrate. We start with the same homogeneous flux of 8Ks hitting the first electron. Again, we see that the electron changes the composition of the K flux, and 5K minus and 3K plus pass on towards the second electron. From the side of the first electron, the second electron will absorb roughly 6 out of the 8 Ks, while it absorbs only 5 out of 8 Ks from the other side. With a net surplus of 1 hit from the side of the electron 1, it is evident that particles with equal charges will repel each other, and the effect must be mutual. This leads to Coulomb's law. Note that it is not the photon which carries the electrostatic force in general. This is quite obvious, since the photon has no attractive properties. Hence, it cannot explain why two opposite charges are attracted to each other. In a universe without any attractive forces, we need a force by proxy to perform attraction. Only for certain types of long-range package transfer do we see photons as real carriers of a subtype of electric force. This interpretation should not contradict quantum electrodynamics. It only specifies what the virtual photons really consist of.